guys, today we're going to be looking at Chapter 8, Lecture 18, Learning Objective Number 1. In Learning Objective Number 1, we are looking at Lewis dot symbols. So the first thing I really want to talk about before we get into that, though, is a review of chemical bonds. So a chemical bond is something that holds two atoms or ions together. So a interaction that holds two atoms or ions together. When we're talking about chemical bonds, we usually look at the following three: ionic bonds, covalent bonds, and metallic bonds. Our ionic bonds are going to be between two ions. This is a bond between two ions. And the bond itself is electrostatic interaction between those cations and anions. So opposite charges attracting to each other. Okay. Our next is a covalent bond. This is going to be the bond between two nonmetals. And this is going to be formed through the sharing of a pair of electrons or pairs of electrons. So an electron pair or pairs shared between two atoms. So they will basically go into the orbitals of these atoms, of both atoms. And then our metallic bond is a little bit harder to explain because we don't really think about it between two atoms. We think about it between many metal atoms. So this is going to be many metal atoms sharing valence electrons. So this would be a bond between many metal atoms. And this is going to be many metal atoms sharing their valence electrons. And this is atoms, not ions. I forgot to note up here, this is a metal cation, non-metal anion. Okay, sorry. Back down here, many metal atoms sharing valence electrons. We call this a sea of electrons. We have electrons delocalized around the atoms. So the electrons are delocalized around the atoms. And they're all shared, and we call this a sea of electrons. And this is what holds the metal atoms together. Okay, so now that we know what we're talking about, type of bonds, because this chapter is all about bonding, let's start back a little bit and look at something called a Lewis dot symbol or Lewis dot structure. So when we're looking at bonding, which is what we're doing in this chapter, we're generally looking at our valence electrons. Our valence electrons are the ones that are going to be furthest from the nucleus, so they're going to be the ones that are going to be interacting with other atoms more. So they're the ones that are going to do all the chemistry for our atoms. They're the ones that are going to make bonds, they're the ones that are going to just in general interact with the atoms around them. So when we have a Lewis dot structure, this is a way of showing those valence electrons, and it shows how those electrons can bond to other atoms. So it's a visual representation of the valence electrons of an atom or ion. Okay, so it shows how many electrons, and it can be used to predict bonds. Okay, so our Lewis dot structures and our Lewis structures, which we'll look at later, were all developed by Gilbert Newton Lewis. Okay, came up with a lot of important things that we use today. Lewis structures, look at Lewis acid-base theory, look at that in 1212, but lots and lots of important things that Gilbert Lewis brought us. So what happens is with our Lewis symbols or Lewis dot structures, we've got our elemental symbol and it's surrounded by the valence electrons. So the elemental symbol is written. And the valence electrons are placed in quadrants around the atom. So we have 4 quadrants around our atom, or we have 4 quadrants around our elemental symbol, and that's where we're going to put our electrons. Okay, so let's look at something like lithium. Lithium has the condensed electron configuration He2S1. So it has one valence electron. So that is the electron that we're going to be showing in our Lewis symbol. So we write our elemental symbol in the middle, and then we put that one Lewis dot there. Okay, let's do another example. Carbon. Carbon has the electron configuration He, 2s2, 2p2. So these are our valence electrons, and there are 4 of them. So we put our carbon, and now we're going to place electrons around. The first one was really easy because we just placed one. There's only one. Remember that we have 4 quadrants. So I usually kind of divide the atom like that when I'm drawing my quadrants. I find that to be the easiest way. You can do it as a T if you would like. And you're going to add in electrons singly before doubling them up. So 1, 2, 3, 4. So it would look like this. Okay. So hopefully what we can see from here, we have lithium. Lithium is not going to really want to bond in a covalent nature. So it'll probably just lose this one electron, which is what it does. With carbon, it is going to want to covalently bond. So it's probably going to try and find a partner for each one of these lone electrons. Okay. Um, Note that a covalent bond a single one, is a pair of electrons. So right now we only have single electrons around our carbon. So in order to be happier, it's going to want to have pairs around it. So it's going to try and form 4 bonds. Okay. So it's pretty easy to draw these. You can do them for ions or atoms. Your steps pretty easy. You're gonna write your elemental symbol, right? The elemental symbol. After you have written the elemental symbol, you're going to count your valence electrons. If you have a cation, you're going to remove valence electrons equal to the charge. So if you're starting with a neutral and going to a cation, you remove those valence electrons. If you're starting from neutral and you're going to an anion, you're going to add electrons equal to the charge. Next, you are going to place electrons around the the elemental symbol. In quadrants. But when you're doing this, make sure to add the electrons in singly before we double, before pairing. And then lastly, if you have an ion, you're going to add brackets with and include the charge. Okay. One last thing before we do a true example is bringing in the idea of the octet rule. So a lot of our atoms, especially our earlier atoms, are going to want to be stable. And to be stable, they need to have a empty or filled outer shell of electrons. So our atoms are most stable when their outer shell is filled or empty. Okay, so this is the same as what we see with a noble gas. So noble gases have a stable number of electrons because their outer shell is filled. Because of this, most atoms, if they are not a noble gas, are going to try and get a noble gas configuration. So atoms will try to achieve a noble gas configuration, noble gas electron configuration, in order to stabilize. Okay, so if we have something like hydrogen and helium, their noble gas that's close to them are helium, so they're going to try and have 2 electrons in their outer shell. So to have a noble gas configuration for these, means that their S shell, their one shell is filled, so they have 2 electrons to fill their outer orbital or outer shell. Most everything else is going to want something a little greater. So other atoms, so n equals 2 and above, they are going to have S and P, which means that they are going to want to have a filled outer shell of 8 electrons. So their noble gas configuration need 8 electrons to fill their outer shell. That's because we have S2, P6, so that's where we get that 8 electrons from. We don't usually do anything beyond main group, so we don't really think about the D, and the D isn't generally outer shell because it's always a lower shell value. So this 8 electrons is where we get our octet rule. So when an atom has a filled outer shell, so this is our S and P filled, our D, um, our D and F are going to be lower shells, so we're not considering those. But when we fill up those S and P subshells, we have 8 electrons, which is our octet. An octet is very stable. So if we can get 8 electrons around an atom, this is a stabilizing effect. Okay? So, ionic compounds, or ionic compounds achieve an octet by the metals losing electrons and the nonmetals gaining electrons. We can think about something like sodium chloride. Sodium has an electron configuration of Ne3s1. Chlorine has electron configuration of Ne3s2, 3p5. This has one too many electrons to have a empty outer shell. This has one too few electrons to have a filled outer shell. So we subtract one electron here. We add one electron here. And we get a empty outer shell and a filled outer shell. So we get Na plus, Cl minus. And looking at it like this, we could write our Lewis symbols like that. And then our covalent compounds and molecules achieve this by sharing electrons. For instance, we have our carbon with our 4 electrons, and then we add in things that also have electrons. And what we get is our covalent bonds. And here we have 2 electrons, 4, 6, 8. There is our octet around our carbon. Our hydrogen does not need an octet because it only wants 2 electrons around it, but each of the hydrogens have 2 electrons. So that is how we achieve an octet when we are talking about covalent substances. So now the question is, what is the Lewis symbol for phosphorus and phosphorus 3 minus? So phosphorus has an electron configuration of an E3s2, 3p3. So we see from this that it has 5 electrons in its outer shell. So we're going to put our phosphorus in the middle. 1, 2, 3, 4, and 5. So phosphorus will want to make 3 bonds in order to get to an octet. And then if we have P3 minus, we add 3 electrons in, giving us a electron configuration of Ne 3s2 3p6 1 2 3 4 5 6 7 8 for those 8 electrons right there. And because it is a anion, we put brackets around it with the charge given at the top right outside of the brackets. Okay, and we can see here we have 1 2 3 4 5 6 7 8. So its octet has been achieved. Okay, that's everything for this video.